Okay, so today we're going to talk about related rates. And practically, when we are working with related rates, our goal is going to be um, to basically, so let's say the goal of this section is to create an equation that describes a particular problem. And when we find the equation of this, or the equation that we create that describes this particular problem, usually that equation is going to be described with respect to time. And basically, once we do that, once we come up with the equation, then we want to solve for the unknown. Okay, and what you'll notice is, especially in this class, the way we're going to need to solve for the unknown, this is going to be done usually finding the derivative. Okay, so what you'll notice is the goal here is going to be we'll be asked to solve for a certain problem, and we need to come up with an equation that describes it. And you'll notice that that equation is affected with based on time, and then we find the derivative to help us solve for the unknown. So let's actually talk about kind of like the steps involved in solving these related rates type problems, and then we will do an example where we'll put these steps to use. Now, look, these steps that I give you, you don't have to literally follow them step by step, but these are kind of like some crucial steps that are helpful to solve these problems, okay? So the first step, I think this one's kind of obvious, where we say read the problem carefully. And what I mean by this is there's going to be a lot of information given to us. So pay attention to the given information, and specifically pay attention to what's being asked of you to find. So there's going to be a lot of information. So you need to make sure that you carefully read the problem, write out what's given to us, and then after we write that out, then we can kind of try to put that to use. Now, the second step is crucial for me. Since I'm such a visual learner, I always like to draw a picture that describes the scenario, okay? Now, you might not always be able to draw a picture, or you might not need to always draw a picture, but for me, drawing a diagram would be of most benefit, because it just makes, if I could draw a picture that describes what's going on, then I feel like I can solve this problem much more effectively or efficiently. So for me, you'll notice anytime we work on related rates, the first thing I'm going to do is, after I kind of write out what's been given to me, I want to draw a diagram if possible. Okay. And then the third step is write an equation that relates the various quantities oh actually, sorry, let's get rid of the third step. I made a mistake. I jumped to like step number 5. So let's hold off on that. The third step is introduce notation. And what we mean by this is, when you read the problem, the given information or the unknown, so you're going to introduce notation that describes what it is, what information is given and what hasn't been given. So what we want to do is we want to assign symbols or variables, basically, to all quantities that are a function of time. So basically, we're saying, look, give symbols to the given information and what we're trying to find here, okay? And then what we want to do is the fourth step, express the given information and the required rate in terms of derivatives. So if you were wondering, steps 3 and 4 are very similar because, see, we're introducing notation in step 3 as we are in step 4 as well. Except in step 4, we're specifically saying that, hey, some given information will be in terms of derivatives, okay? So how do we know? Because we know derivatives are rates of change. And to be more specific, instantaneous rates of change. So if I tell you that the rate of, I don't know, let's say the rate of the volume of a cube is changing at 2 cubic feet per second, for example, then I'm giving you dv dt. So I'm giving the change of volume with respect to time, because every second that goes by, I'm losing 2 cubic feet of volume. Okay, so anytime you see rates, those are derivatives. So make sure to use the proper notation. Like, see, we know dy dx means the derivative of y with respect to x. However, in this section, our variable is going to be time. Our independent variable is time. So if I'm describing rate, it's going to be something like dy dt or dx dt or dz dt. Notice how x, y, and z and what I just gave you, those are my dependent variables, and time is the independent variable. So once you've introduced your symbols and you've identified what your rates of change are, or you've basically assigned your variables and so on in steps 3 and 4, in step 5, now we're ready to write an equation using the given information. So step 5 is write an equation that relates the various quantities of the problem. So what you'll notice is, based on your given information, you'll have a good idea as to what equations to use. And these equations that we're talking about, you've seen them before. For example, the Pythagorean theorem and different types of formulas, like volume of a sphere or volume of a cube or whatever it may be. So just remember, what's going to happen is, based on what information is given and what's been asked for you to find, you could write an equation that relates to various problems. Now, what I want to point out here is, let's make a comment here, or let me finish off the 5th step and then we'll make a comment on this. There's a very important comment that I need to make here. So if necessary, use the geometry of the situation to eliminate one of the variables by substitution. So here's the nice thing about related rates. We can write an equation that has 5 variables, for example. And if you think back to previous classes, we didn't really like to have too many variables. In fact, we did whatever we could to minimize the number of variables we have. However, in this section with related rates, if we can basically minimize the number of variables we have, like if we could substitute something to be able to eliminate one of the variables, we'll do that. But if we have an equation with like 3 variables and we can't break down those variables to a smaller number of variables, it's okay. We could still solve these problems because there's probably still enough information given to us that allow us to solve the problem. Okay, so what I want to do is, let me go on to the next page. For step 5, I want to make a comment here. So a note I want to make. And this is actually very, very important. So the comment I want to make is, always write a generic equation for step number 5. So what do I mean by write a generic equation? Don't plug in specifics until the end. So in other words, do not plug in specific values until after the derivative has been found. Okay, the reason why I'm saying this is, if I plug in my values, my given values, prematurely, what's going to happen is eventually I'm going to have to take the derivative. And if I plug in my numbers prematurely, once I plug in a number for a variable, it becomes a constant. And when you find a derivative of a constant, it becomes a 0. So we start losing important characteristics or important aspects of the problem when we plug in prematurely. So what you'll notice is, we pick the specifics until we leave the equation as generic as possible, and then we plug in specifics until the end. Okay, the only time you could plug in specifics from the beginning before you find a derivative is if that value never ever changes. But if the value is constantly changing, then that means that's a specific value that we'll plug in at the end after we find a derivative. Okay, so you want to keep from plugging in specifics until the end, just so you don't miss out on important quantities of your equation. Okay, so once we do that, once you write your equation and you write your generic equation, then what you're going to do is you're going to find the derivative of that equation so you could answer your related rates question. Okay, so there's basically, in step 6, we're going to use the chain rule. And you'll notice, I mean, I'm writing chain rule here, but you'll notice once you find a derivative, you'll notice that the chain rule is involved. So it's pretty common that we're using the chain rule over and over and over. And if you notice in this class, the chain rule is applied quite a bit. Okay, so use the chain rule to differentiate both sides of the equation with respect to t. Okay, and then once you do that, once you find the derivative, now we can plug in specifics like the given information. So notice how the last step, which is step 7, we're substituting. And notice how I made a comment about this earlier. Then you substitute the given information into the resulting equation. And then you solve for the unknown rate and solve for the unknown rate. Okay, now one thing I want to point out is, you don't have to number your steps when you're solving these related rates problems. I just numbered them for you so you kind of see what it is we're doing. So just to briefly summarize, when you read the problem, you want to write out all the given information. And of course, you also want to kind of identify the appropriate derivatives. Whenever they talk about some rate of change, that's your derivative. Okay, so once you draw your picture and you label all the parts, you assign your variables and you kind of assign the notation to the given information. Then what you do is you try to write a generic equation that describes what it is you're trying to solve. So usually the given information and what you're asked to solve for, that will direct you towards the appropriate equation. And like I said, the equations you're going to use aren't anything new. Like you've seen these equations before. And then once you write your generic equation, then you find the derivative. And then once you find the derivative, then you plug in specifics to answer your related rates question. Okay, so let's look at an example, and then that'll basically pretty much wrap up this section. But remember, we're going to have a lot of practice in this section throughout the next few days. So here's what's happening. So air is being pumped into a spherical balloon so that its volume increases at a rate 100 cubic centimeters per second. The question is, how fast is the radius of the balloon increasing when the diameter is 50 centimeters. Okay, so let's take a minute here and kind of think about what's happening here. So what we know is we have a balloon, so it's a spherical balloon, so it's a circular balloon, okay? And the radius is r. Now notice how I'm labeling this very generically. How come? Because as I'm pumping air into this balloon, it's getting larger and larger and larger. So r is constantly changing. So the radius here, I'm leaving as a variable, okay? And so, in fact, what do we notice here? As the radius changes, as we pump air into this, the radius changes. So the goal here is to find out at a certain radius, what's the rate that's changing. So that'll come in at the end, okay? So let's see what's the information that's being given to us. So we have air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. So here's the first piece of information. What have they given us? They're giving us the rate of the volume. So basically, remember, when we talk about a rate, we're talking about derivatives. So the rate of the volume, which is the derivative of the volume, and it's with respect to time because look, it's cubic centimeters per second. So the first piece of information, which is right here, is what? It's dv dt equals to 100. Because what are we saying? The rate of change of volume, which is the derivative of volume with respect to time, is 100 cubic centimeters per second. Now, by the way, my volume is positive. How come? Because I'm pumping air into the balloon, so the volume is increasing. So if I was letting air out of the balloon at 100 cubic centimeters per second, then my dv dt would be negative 100. So pay attention to rates of change. Rates of change could be negative also. So if something is increasing, if your rate of change is increasing, then the derivative is positive, okay? So the given information is this, okay? So it doesn't look like anything else is given. So it doesn't look like much has been given to us. Now, what is it that we're trying to find? So they're asking us to find what? What is it that we want? We want to find, so how fast is the radius of the balloon increasing? Now look, how fast is the radius of the balloon increasing? So notice how they want us to find what? The rate of change of the radius, which is what? Find dr dt. Okay, so this is what? The rate of change of the radius with respect to time when the diameter is, so when d equals to 50 centimeters. And so look, this is my specific, isn't it? The diameter is 50 centimeters, which means if the diameter is 50 centimeters, in terms of the radius is 25 centimeters. But see, this is the specific. It's saying this balloon, you're pumping air into this balloon. The second the radius of this balloon is 25 centimeters, how fast is the length of the radius increasing? Okay, so this is the specific. So remember, specifics we don't plug in until the end. Okay, now look, based on this given information and what's being asked for us to find, what formula do you think you'd need to use for this balloon? So take a minute, think about it. If you want, you could pause the video and then press play again. But if you've thought about it long enough, notice how we have some information about the volume of the balloon changing, and then we have the radius. So sure enough, based on the information that's been given to us, we want to use, so for the equation to use, it should be what? The volume of a sphere. Okay, and so what is the volume of a sphere? You should all know this. If not, make sure to memorize these basic formulas, which is V equals to 4/3 pi r cubed. Now look, here's the problem. I don't want to plug in 25 for radius just yet, because if I plug in 25 for radius, then this whole thing will be a constant. So to find the rate of change of the volume, it'll zero out, which that makes no sense. So here's what I want to do. I want to put this to use. I want to put dv dt to use. And in fact, what you should notice is when I find the derivative of this, I need dr dt somehow to show up. Now, what is dr dt? That's the derivative of the radius with respect to time. Now, if you look at this right here is all changing with respect to time. See, as time goes on and I pump air into this, isn't the volume changing with respect to time? So as each second that goes by, the volume increases. So notice how I'm using implicit differentiation here, because I don't know what the equation of the volume is with respect to time, and so is the radius. The volume and the radius both depend on time. So when I find a derivative of volume, I'm finding it with respect to time. And when I find a derivative of the radius, I'm finding that with respect to time, because the volume and the radius both change with respect to time. I hope that makes sense. If it doesn't, ask me to clarify tomorrow in class as well. So let's do this. Let's find a derivative of this. The derivative of v will just be what? dv dt, which, what am I saying? The derivative of v with respect to time equals. Now, this is just a constant. Remember, constants tag along. Now, to find the derivative of this, I have to use the chain rule, because the outside is the exponent, the inside is the derivative of the radius, which, remember, the radius depends on time because it changes with respect to time. So let's basically find the derivative of this. You bring the 3 out front, so it'll be what? 3 times 4/3 pi r squared times the derivative of the inside, which the derivative of r is what? It's dr dt, because the radius is changing with respect to time. So remember, v and r both depend on time. So that's why you'd say the derivative of r, I don't know what it is, so I call it dr dt. Now, let's simplify this a little bit. But the good news is once you do this, now you can plug in specifics and you have everything you need. So this becomes what? dv dt equals to, the 3's cancel out, so we get what? 4 pi r squared dr dt. Okay, now here's my equation. Now look, here's the good news. What am I trying to find? We're trying to find dr dt. And if you look here, there's my dr dt. And what do I need? I need dv dt, which is 100, and I need r, which is 25. So now I could actually plug in the specifics. So what is this going to tell me? Let's plug in the specifics and see what we get. So if I replace dv dt with 100, I get 4 pi, plug in 25 for r, 25 squared, dr dt. And now I could solve for dr dt. And if I do that, what do I get? Well, if I divide by 4 pi, so let's not simplify this. I think we could cancel things out. So if I divide both sides by 4 pi over 25 squared, I get what? dr dt equals to 100 divided by 4 pi times 25 squared. So what do I notice? The 100 and the 4 cancel out. This is 25. And the good news is one of the 25s cancel out. So I actually get 1 over 25 pi. And what are the units? It's centimeters per second. So what are we saying here? What is this answer saying? It's saying, look, you're pumping, so we have a balloon here. I'm pumping this with air, okay? The second that the radius is 25 centimeters, the radius then is then increasing at a rate of 1 over 25 pi centimeters per second, which, yeah, I think this is like so cool because we're actually finding the exact rate in which how fast this radius is increasing once the radius is 25 centimeters. And see, just like those balloons, anytime you blow up a balloon, it first initially it increases faster, and then the larger it gets, then it increases, the radius increases at a slower and slower rate. So you could see that the smaller the radius, like if you, let's say, plugged in 10 for r here, your dr dt would have been bigger than 1 over 25 pi, because at that point dr dt is increasing much faster than it is as opposed it is when it's 25 centimeters, and so on. Okay, so just to quickly summarize what we did, we came up with the equation, we labeled all the given information, so dv dt, which was the rate of change of the volume, and then we were asked to find the rate of change of the radius, which was find dr dt. Now look, why am I calling this dv dt and dr dt? Because the volume and the radius both change with respect to time. So if you think about it, time is my independent variable. So anytime I'm finding derivatives, I find with respect to time. Now, once we did that, then we had the given information, which we're saying the diameter was 50 centimeters. How fast is dr dt changing? So when I found the equation here, which we discussed about what equation we'd use the volume formula. And when you found the derivative of volume, see, the reason why we called it dv dt is we're using implicit differentiation. We're saying, look, volume is a function of time, and I don't have it in terms of time. So whatever volume is, find its derivative with respect to time. And then you'd say the same thing about the radius. You'd say, look, the radius is also a function of time. It's changing with respect to time. So I need to find this derivative implicitly with respect to time. And you notice the chain rule is involved. So to find the derivative of r cubed, I first had to bring the 3 out front, which then becomes r squared. Then when you find the derivative of the inside, which is r, you just call it dr dt, because remember, r is a function of time. I don't know what r is in terms of time, but I know that the derivative of r is dr dt, because both of these guys are changing with respect to time. And notice we don't even really care to find the derivative of the volume or the radius with respect. We're just calling them dv dt, dr dt. So once you do that and you simplify it, then you plug in specifics. See, dv dt was given to us. Dr dt was what we're trying to find, but r was given to us. So we're saying the instant that r is 25, what is dr dt? How fast is the radius changing? And once you did that, we found out that this was the problem. Okay, so we will be solving a bunch of different types of problems that have to do with related rates. So you'll get plenty of practice with this. So keep that in mind. Like I said, at first it might be a little weird, but with more practice, which we'll have plenty of practice on this, you're going to get better and better at this. Okay. So, and one other thing I want to point out, notice how I didn't number the steps. But if you kind of look at this last example I did, we pretty much went through all 7 steps. Okay, but you don't have to number them. Remember, this is just to kind of, it was just to help you organize how to work through these. Okay, so that takes care of this section.